Hi, welcome back to the last section of the course. Okay, now what we're going to be looking at today is engineering solutions to connect output devices to our microcontroller. So we've looked at the fact that we might turn LEDs on and off, for instance, but how do we engineer a solution to connect an LED to a microcontroller? Is it straightforward, or is it less straightforward than you might think? So we're going to look at how we might use the specifications of microcontrollers and LEDs to figure this out. So let's start with a hypothetical first of all. Say we've got a simple AA cell, 1.5 volts. We're going to connect it to an LED, assuming we've got the polarity correct, okay, positive of the cell to positive of the LED, negative of the cell, negative of the LED, then what we've got there is something that won't work. Okay, now typically LEDs require at least 2 volts to run. So we know we've got 1.5 volts, so this won't work. Well, so you might think, well, actually, let's just double that voltage because we've got 2 cells. We'll put them in series. That gives us 3 volts. Well, actually, it gives us anything from about 1.8 volts if the cells are pretty flat, through to maybe 1.7, about 2.4, 3.4 volts actually, if we've got 2 cells connected in series. And that's probably too much for our LED. You try it at home. LED might work. It might change color a bit and then stop working. So next we want to figure out, maybe that won't work. Well, what will work in terms of connecting a microcontroller to an LED? What do we need to do here? How do we need to know? Well, actually, to do this, you need to know the characteristics of the output of the microcontroller, and you need to know the characteristics of the LED. And so this we're going to look at in detail now, okay? So let's have a look at the characteristics of an LED. So in the assignment, I've told you to look up LTL4223 from DigiKey, download the data sheet. I've crossed this out of the notes because we're going to work with this one. So let's have a look at this. Typically, this LED requires 2 volts and 20 milliamps will flow. So you connect a 2 volt cell, 2 volt source to it, then 20 milliamps, there'll be 20 milliamps of current flowing through the LED, and it'll be a certain brightness, and typically that will be about its standard sort of brightness. Okay, so now if we have much less than 2 volts, then it probably won't work, and if we have much more than 2 volts, then it will die. Okay, it will die. But typically our microcontrollers are running at 5 volts, so what we need then is to figure out that what is the resistor? What is the resistor that goes between our microcontroller and our LED? And so what I want to do is I want to think about this equivalent circuit model here. And so what I want to do is I want to jump back to the notes from 1.1 and just do a really quick introduction to the equivalent circuit model again. And I'll pop these 2 pages up as well on the website. So basically, we've got this complex unknown circuit. We don't have to know everything about it. We can just know what its terminal characteristics are. What does it look like to something that's connected to its input? And if we connect something to its output, what sort of thing is feeding it? And so we can look at this in its abstract form. And it's really simple, actually, for a DC circuit like this. It's not hard. All we can do is think about the input of our circuit being a resistance and the output being a source and a resistor. This is the Thevenin equivalent, of course. So let's just think about what actually is inside our microcontroller. So what's inside our microcontroller is this complex circuit. So what we've got here is, say this is operating as an input, then we've got some input device connected to this, and this is our input circuits, and takes it through to the bus, okay? Well, all of this can be ignored and replaced by a simple resistance, okay? So our simple resistance will be, let's just get rid of those. Our simple resistance will be this. And in actual fact, for our microcontroller, this is typically very high. And we can think of it in most situations as an infinite. Okay, it's much higher than what we're connecting to it. It's not going to create any loading effects on our sensor circuit. So we can use this quite reliably. It's quite good for most purposes. But what about this output circuit? Let's have a look. What we've got here is we've got some sort of source, which is a voltage, right? Now, this is our port register, so it comes off the data bus, gets stored in the port register, goes through this if it's configured as an output, and then goes out to our load. Okay, so all of this actually can be replaced by a source and a series resistance. Okay, and that's really the fundamental understanding of save-ins, and this is why our equivalent circuit model is so powerful. So let me just scratch those and think about, well, what is the source and what's the resistance? Well, actually, the source of our circuit is fairly simple. It is just VCC. So our source here is this amplification is really nothing. It's either 1 or 0, because that's what amplification is in a microcontroller. And Vin is actually, well, it's VCC. So what we're looking at here is the VCC being switched on and off, and we've got some finite resistance. And actually, this is a finite resistance in a microcontroller. We cannot ignore it. Okay, it could be as low as 10 ohms, or maybe even a bit lower, but it won't be 0, and it will have an impact upon whatever we connect to the output circuit. And so how do we measure that impact? Well, we know this already. Okay, so let's just review that. What we've got here, of course, is we've got some circuit which is connected to some other load. And we're going to connect a load to our microcontroller. And you can think our load itself can also be replaced by its equivalent resistance. And then we can think, well, hey, this is really simple. This is just a voltage divider. And when we look at it, all you can see is that this output voltage here is going to be a little bit less than our VCC voltage in our microcontroller, because this has some finite resistance. In amplification, we might have a low voltage, but here we say we've got 5 volts here, and we've got a ratio of resistances here between 1 and 100, then we're going to find that this voltage is a little bit less than 5 volts, okay, because some of the voltage is dropped across this. And we work that out by simply using our voltage divider, understanding the model for a voltage divider, which works really well. So that's just a really brief back introduction to the equivalent circuit model. So what we're going to look for is we're going to try and figure out what this looks like for a microcontroller and what this looks like for an LED. Now that's an interesting concept. So let's jump back to those notes. So let's think about this LED. Now I'm going to zoom in on this and scroll back down, try not to make a mess of it. There we go. Right. We've lost it. Here we go. Here is our circuit. We're zooming in on this graph. So this here, this graph explains what happens when you connect voltage to an LED. Well, you know it glows, okay? And we know that below a certain voltage it won't glow, and above a certain voltage it will blow up. So we're really only interested in this middle sort of section of the graph. And you can see, looking at this, that actually this almost appears like a resistance. Because if we plot voltage against current for a resistor, we get a straight line from 0 going up. But in this case, of course, we don't start at 0, we start at some other value. And during this process here, as long as our voltage stays within this sort of range, we're going to get a nice linear transfer characteristic. We're going to see that the current and the voltage are related by a straight line. Now, this doesn't always happen with LEDs. Some of them have curves. And so what you do is you pick the range at which you're interested, and there might be a bit of a curve here. Well, you just pick the bit of the range that you're interested in, and then you work it as if it were a straight line. Okay, that's the easiest thing to do. Don't get too complex with this, because these LEDs are mass manufactured, and really their properties range over a bit of a spectrum. And so this will be a typical characteristic. And that's what you'll find in these data sheets is typical characteristics. You won't find that every LED is exactly the same, even as it comes off the production line. There are subtle differences in them. And it's a bit like resistors. When you buy a resistor, you see a resistor isn't exactly 10 ohms, but it is actually 10 plus or minus some percentage. And we typically buy 1% resistors nowadays. So a resistor will be plus or minus 1%. Well, here, of course, an LED might be plus or minus a couple of percent. And so what we're going to do is we're going to think about the LED just over this range here. So what is this range we're looking at? Well, actually, I've looked at this and I've put it up here. We're looking at the voltage over the current. Now I'm not looking at this and trying to work out the equation for this line, okay? Now that of course will be delta y over delta x. But what we're looking at is voltage over current, which is delta X over delta Y. So we're looking for the resistance. But we know, of course, that that is just the inverse of the slope of the line, delta Y over delta X. So we'll just look at it straight away. Voltage over current, that's our resistance. So what is the voltage? The voltage over this range I'm saying is from, well, this is saying, I'm saying this is 2.3 volts. So let's just have a little draw of that sort of thing on the graph. So what we've got here is I'm saying that this here is 2 volts, 2.2 volts, 2.4 volts. So this is close enough to 2.3 volts here, okay? And at that point, it's 10 milliamps. And at this point here, well, this is 1.8 volts. This would be 1.9 volts. So I'm saying that this point here is actually 1.85 volts. So 1.85 volts, we get 10 milliamps. Sorry, previously made that mistake. 1.8 volts, we get 10 milliamps. 2.3 volts, we get 45 milliamps. And so let's just put this straight into our a calculation for using Ohm's law, which is, but as long as we realize it is only valid over this range of values, okay, that's fine. We're only using it over this range of values. And as I said, even if this was a bit curved, we would think of it as a straight line close enough for what we're doing. So I'm figuring out that actually this is 13 ohms. This looks like a 13 ohm resistor. That's exactly what it is. So that's not a hard thing. It looks like a 13 ohm resistor. But of course, the 13 ohm resistor only is 13 ohms over this point. And so what I want to do is just do a little bit of thinking about this. If I pull this line all the way down to where it cuts the this axis, I'm saying that that cuts at around about 1.7 volts. So what I've got here actually is if I think of this as a very square characteristic, and I can do this because I'm really only interested in this part of the curve, which is linear-ish. And I can say that actually what this looks like is that once we exceed 1.7 volts, this acts like a resistor. And there's the clue as to how we will model it. Once the input exceeds 1.7 volts, we can model this as a resistor of 13 ohms. And so what we have here is we create a simple model for our LED. And this is, yes, it is a simplistic model. If you're going to be a scientist and you're going to design things for LEDs, you might come up with some more complex models than this, I can tell you. But all we need to know as engineers is that we can think of this as a simple source of 1.7 volts and connected to a 13 ohm resistor. So what that means is that if our electric potential here is greater than 1.7 volts, this is 1.7. If this is greater than 1.7, then there will be charge flow, right? And it will flow in this direction. So this is where the current will go. And what that means is the LED will glow. Now we know, of course, that really it's going to start at a little bit below 1.7. It's going to start at 1.6, and there'll be some charge, and then it will get into the linear part of it around here somewhere on our curve. Okay, so what we're saying is that if it's 1.7 volts, and this is a resistance of 13 ohms, then we can actually just consider this as once this goes above 1.7 volts, we will have a linear resistance to deal with. Of course, it isn't 1.7, but we're only going to be looking at the values on the curve which are within our range of interest. And that's really important because a resistor will be completely linear over its whole range, but this LED will only be linear over this part of the range. But that's good enough model because we're only interested in, you know, somewhere between 10 and 45 milliamps, okay? So now we can actually work out that we've got a 13 ohm resistor here, and we've got a 1.7 volt source. Now, volts,